Welcome back. This is yet another class in the electronic systems packaging course. We are almost at the end of chapter 1. As you know, chapter 1 or module 1 is related to or entitled overview of electronic systems packaging. So, we have seen very many basic fundamental items or ideas and definitions. So, I hope you are on the same page as I am. So, that we will now move to the next chapter after finishing a few of the final conclusive items in chapter 1. Now, if you want to recap a bit, which is I think much better, what we have seen in the last class is all the levels of packaging we have seen. So, if you recollect, we have seen what level 0 is, level 1, 2, 3 and 4, and you by now must be very familiar with what are the exact areas falling under each of these levels of packaging. Now, we also started looking at some case studies. If you recollect, the first case study, this case study is about product packaging, right. This case study is about examples of product packaging. So, what a design engineer should really look into if you are concerned with the design of product from start to finish, including mechanical aspects. So, the first case study application area that we looked at was mobile phones or cellular phones, right. We saw all the various items including the economic factors, cost and so on. So, manufacturing is related to cost. I think we are very clear about these packaging aspects. The next part of the case study or the next example that we looked at was personal computer, right. Personal computers including low cost PC. I mentioned to you before a very important phenomenon that depending upon the area, the cost of the product is determined through design, and in manufacturing accordingly the materials are chosen. So, in personal computers, if it is a desktop computer, then you will look at various angles to fix the cost, and accordingly the packaging also takes place. But for a low cost, we also saw how to make it low cost by choosing different set of materials and choosing different packaging aspects. Today, we are going to look at the third example in case study, and that will be in the area of automobiles. So, example 3 that I have given here now is automotive electronic systems. These automotive electronic systems present a very difficult operating environment. I hope you can agree with that. When we say environment, the application area and the environment with which it is put to use day to day. So, we are considering here when we say automotive electronics for our very simple understanding and a car, okay, because we have to look at volume operations, volume manufacturing, and for us the best example will be an automotive system like a car. Typically, there are long lead times to develop an electronic system for this application, develop tools and qualify before production. High level of technical and personal support is required, and low profit margins. Why do we say low profit margins? Is because if you compare a cell phone or a mobile phone industry, the volumes here in automobiles are definitely less compared to the other industry. Therefore, profits will come only if you keep the price tag very high, and for that the electronic systems will have to be high end performance, and for that you will have relatively very few customers taking it. So, these are all interrelated: cost, volume and the level of packaging or the level of technology that you have integrated into the electronic system. So, please remember this item very much for automobile systems. Automotive electronic systems can be classified into engine control and management systems. We have seen these points earlier, but I will try to put it back again. Transmission controllers, lot of circuit design has to go into transmission controllers, cruise controllers, these are all placed under the hood. Okay. Please remember this term under the hood. Under the hood products, under the hood applications, because under the hood of the automobile the environment is very harsh. The temperatures are very high, there can be atmosphere which can be corrosive in nature. Therefore, your electronic products need to be packaged and enclosed in such a way that they will not be affected by these environmental conditions. Braking controllers, traction controllers, suspension controllers, lighting, wipers and air conditioning systems, heating systems, electronic dashboard and mirrors, and probably this will be the place where most of your information from other parts of the automobile will be displayed. So, the electronic dashboard is a sort of a convergence area for display, right. So, most of the display, whether it is a tire pressure information or fuel condition and status, or whether all of these above systems, controllers and so on, the engine level, the brake conditions and so on, everything is going to be displayed at the front dashboard, and therefore, a lot of electronics up to this point will have to be looked at. Safety electronics, that means safety devices need to be monitored and they should function reliably when such a situation arises. Convenience and entertainment systems, these are all very required categories of applications in automobiles. What is the nature of automotive electronics? As a design engineer, I think you must look into improving technologies in these areas, and these are the current status. They have about 40 to 50% content of non-integrated components like connectors, sensors, relays, wire harnesses. This is going to take a lot of space under the hood and around the car. Actuators, lamps, etc. Architecture is significantly influenced by the non-electronic components. So, if you look at automotive electronics, you can safely say that the active devices will be much less compared to the electromechanical components like relays, sensors, connectors and so on. And they also harness a lot of wire throughout the system. In this case, the system is the automobile. So, you can expect lot of wiring to take place, okay, because right from the under the hood to the end of the car, to the side of the car and inside the car, you have to do a lot of wiring and they have to be reliable. So, these are the conditions for automotive electronics. Now, as a design engineer, please have a look at the choice of components. Be very careful in selecting what type of components you have to choose for this application. The choice of components for this application will be different to that for a mobile phone or a PC or any other handheld product, because the component has to work in a rugged condition, and therefore, you have to look at the packaging of such an active device or a passive device that you are going to use. So, you have to look at reliability of these components under these conditions. Packaging design of boards. So, obviously, you are going to use a board, a PCB like this that will be used for an automobile. So, let us say this PCB which is going to be used for the automobile will have to have a different set of conditions and packaging phenomenon different from other systems. Why should it be different? For example, there are different types of printed wiring boards or printed circuit boards. Now, there are two terms that I have used so far, you would have understood. One is a printed wiring board the other is called a printed circuit board, PCB. If you look into the literature or the web, these terms are used interchangeably. So, there might be some confusion for you to apprehend or understand why and when to use PWB, when to use a PCB. I will come to that in a very short while. Okay. So, packaging design of boards. So, how can boards be made more efficient? So, can I use a board which is organic in nature for automotive electronics? Can I use a board which is ceramic or inorganic in nature for automobiles? So, these are the conditions that you have to look at. For example, I am going to show you a board here which has got a bare die on top of it. Now, for an automobile electronics, can I use a bare die and a thin laminate like this? Will it work reliably? So, these are the questions that a design engineer should know. Obviously, you do not want to use a bare die, you want to use a package die. So, an example for a package die will be something like this. As you can see here, this is a package die. This is a plastic package. Therefore, a plastic package sitting on an organic substrate, is it a very good combination for automobile electronics. Okay. So, these kind of design decisions a company or an industry or a design engineer should take at the beginning before even planning to look at the design aspects of the circuit. Then you have to take care of EMI, electromagnetic shielding, very carefully, because it is working under adverse conditions. Then the environmental conditions, as I have emphasized time and again, there can be conditions where it can go up to 150 degrees centigrade, and typically for such systems you will do reliability testing from -40 to +125 or +150 for the components for the board that is built for automobile electronics, and therefore, before it is sent to the industry and made in large volumes, they will undergo lot of thermal cycling to classify the board as a reliable one. Okay. So, there may be several subsystems of this type in the automobile product. Therefore, you have to make sure that they function for a large number of years. In the industry, people look for high reliability products, and it is much more in automobile electronics. Need to maintain stringent emission regulations. These are outside the purview of electronics, but at the same time your controllers, your the mechanism of working of the fuel injection controller and other subsystems will have a direct reflection on the measurements that is done for emission and so on. Obviously, fuel is the first important thing to have a clean fuel and therefore, a clean emission, but the electronics also plays a great part in monitoring these activities or figures. These regulations differ from one country to another. So, this is the conclusion of third example for product packaging. So, we have seen mobile application, we have seen PCs, low cost PCs, and now we have seen automobile electronics. Like that, we can take different products and try to list areas or points that need to be looked at from the design engineer's perspective, so that you can make a reliable product. Okay. So, I think you can take the reference books from now on and look at other examples. Okay. The examples can be, for example, in the area of medical electronics, okay, and healthcare. So, probably if you take the textbook of Rao Tummala and you can look at chapter 3, you will get such a simple case study for medical electronics. Kindly go through that and you will see what are the important implications of packaging in medical electronics. Okay. So, as a conclusion to chapter 1, what I will now do is give some current trends in packaging upfront. Okay. Instead of talking about current trends at the end of the total package of this video course, I would like to sensitize you to the current trends in packaging upfront, so that you can expect these things to be discussed in this course from now on. So, we have seen semiconductors, and we have seen semiconductor industry growing at an average annual rate of 15% over the period of 40 years. The growth rate is constant. Further reductions from 0.13 micron technology, 0.08 micron technology to the current. I hope you can remember what is the current technology used. We are working at 45 nanometers, and further to 32 nanometer technologies are being used by companies like Intel and so on. So, all of these changes from the previous higher line widths to the current 32, and the future is going to be 22 nanometers or also probably 11 nanometers in about 4 to 5 years from now. All of these require changes in materials and processes. I hope you can appreciate this, because without new materials you can't improve the properties of the devices or the semiconductor. So, the existing semiconductors have some limitations. So, you have to look at new compound semiconductors and so on. At the same time, existing semiconductors can work very well to create lower line widths, but at the same time the equipments related to photolithography and design imprint on the surface of the semiconductors require a lot of technological changes, which is what we are witnessing right now. I have explained in detail what is Moore's law. Now, the question is, as a conclusion to this chapter, will it hold good for the next 5 years? That means, will the doubling of transistors take place every 18 months or at max 24 months. This is what we are going to see. If there is going to be a disruption in technology, or if there is going to be a limitation posed by the photolithography or imaging technique, which I think is a major bottleneck in the semiconductor industry, then the Moore's law might not hold good, in the sense that the doubling of transistors might exceed 24 months, but we are going to witness a lot of technological changes. So, is there going to be another disruptive technology? So, I use the word disruptive, if you can see here in this slide, disruptive technology. Why do I say disruptive? Because a new technology has to come and revolutionize the imaging process. So, that can be disruptive in the sense that entire process can take a new look, okay, and that can be beneficial for the semiconductor industry. The current trends in packaging continuing, I want you to remember some of the terms now. I hope most of you would have heard of the term system on chip. This is more prevalent in the semiconductor manufacturing. That means, you are packing an entire system function on a single chip. So, instead of using 2 or 3 different chips for different functionalities, or due to limitations in manufacturing process, because of current technological changes, you are able to integrate or increase the density or packaging efficiency at the chip level, and the entire interconnections of such a system can be called a system on a chip, SoC. Okay. So, SoC, if you look at this figure, will take place at this level, at the chip level. Okay. Now, let me introduce another term called system in package. How do you define, or what do you mean by system in package? So, if you look at a figure here, you can see that there can be different ICs. An IC can perform it can be a MEMS IC, it can be a RAM, it can be a cache, it can be a memory. Okay. And this particular system in package can house different ICs with different functions. Now, all you do is you can outsource or buy these different active devices and then package them together. For example, a simple figure for that would be you have a simple IC here. Now, you take another IC, this is silicon, this is silicon. Now, we are going to place this silicon on this first silicon device and interconnect it. Okay. So, this can be for example, cache, this can be a microprocessor. Now, you take another device and this is again placed on the same substrate on the it is integrated vertically. Now, this can perform different system function. For example, it can be some other controller card, controller chip. Now, this is again connected to the first substrate, first device. Now, the entire thing can be packaged. This is your package. This can be a plastic package. So, this now becomes a custom built IC. So, this is called system in package. A system in package will perform or is a result of bringing in two or more dies together and interconnecting them, and the entire set of dies are housed on the same substrate. Okay. So, this is different from the multi-chip module concept that we have seen. In a multi-chip module, by textbook definition, the dies are placed on the same substrate, the same plane, but here it is more or less built one on top of the other. So, this reduces space, this utilizes the entire area on the under the bottom die for providing your IOs, okay, and this can be manufactured only by companies that are well versed in creating system in package, because the first level interconnections for system in package are going to be very crucial in determining the reliability of the product. The third term, we will get a chance to discuss system in package much more. So, as an introduction, I think this information is enough right now. When we come to system on package, now it can be by definition, if you look at this figure here, a system on package means you take a printed wiring board, that will be the substrate, an organic substrate can be the substrate for a system on package. Now, you can integrate your MEMS device, your optoelectronics device, your RF device. Okay. You can have multi-layer interconnections using copper, and each of these multi-layers can be connected by micro vias, very small via structures which will connect the various conductors. You can embed passives into the layers of the substrate. So, this becomes a high density package, this becomes a high density interconnect system, and this is on a PWB typically, whereas here you can use ceramic or organic substrates. So, if you look at SOC, SIP, SOP, an SOP can sit on a system in package configuration, and a SIP can become or be part of a module that can sit or mount or be mounted on a system on package. So, today's the most current technological advance is a system on package. So, as I said before, we are going to get opportunity in the next or the third module to discuss about packages, and at that point of time I will be giving you complete information about each of these system in package and system on package. Continuing with the current trends in packaging, if you want to increase the density of your boards or your systems, because board is equal to a system today, because board performs system level functions, then you have to use integrated passives rather than using bulky devices like a resistor and capacitor mounting on the board. So, you can actually build the embedded passives inside the layer. Okay. Now, you can also as a design engineer look into shifting to area array packaging. I think I mentioned to you about peripheral array and array packaging, area array. So, you have to move away from peripheral array packaging to area array packaging to get high densities. Pad densities are up to 100 pads or pins per square centimeter. High density interconnections like the micro via interconnect technology. Now, what is a via and what is a micro via? See, if you take a printed circuit board, for example, I am showing you this board here. This board can be built with different layers of copper wiring. On the top surface here you see you have a single layer of copper, and on the other side you see another copper or other conductor wiring. Now, you have to interconnect from the top to the bottom. How do you do that? You have to create a hole, mechanical hole, and then make it conductive, right. So, that conductive hole is called a via. When I say micro via, by definition in any via that is less than 125 microns in dia. Above that it can be called a simple via structure, but a micro via interconnect technology that is now being used in printed circuit boards has dimensions less than 125 micron. So, you can imagine the size. So, this is very clearly given here in this figure, in this slide. You can see here, if this is for example 1, 2, 3, 4, 5, 6 layer copper wiring, then you can see here a via that is basically interconnecting copper 2 to copper 5, and there is a via that connects copper 1 to copper 2. So, this is a via, and this we call a micro via because it is a very small size, and such vias are used in the semiconductor industry also at the silicon buildup. The same technology is being used at the printed circuit board level. So, there is always a very good similarity between semiconductor manufacturing and PCB manufacturing, which as we go along you will definitely able to visualize and appreciate. Now, if you look at the printed wiring board, I want to spend a few minutes here on the printed wiring board. It is the most important of system level packages. So, we can call this board level packaging. It provides interconnections between devices. It can be an active device or a passive device through the copper tracks, right. So, the basic conductor that is used in this industry is copper. Copper is the best conductor, but we will see when we come to PWB technologies chapter that apart from copper, the basic copper structure is built or strengthened by other conductor devices to enable soldering or attachment. The important thing is it provides a good mechanical support to the components. So, you can see here in the figure or in the sample here which I am showing right now, this is a printed circuit board. You can see various devices, all of them are surface mount, and you can also see very tiny devices. These are all the resistors and the capacitors, very small size, and to handle these you require equipment to pick and place and attach it onto the board. I will quickly show some other examples of PCBs. This is another printed circuit board which is again mounted, and you can see a lot of active devices and you can see a lot of displays on the board. So, this is also an organic substrate. If you look at this board now, you will see that this contains gold finish. You can see the glitter that is from gold. So, the copper is now overplated with gold. So, there are specific reasons why we plate gold, okay, and what the thickness should be for the gold plating and so on. So, you can expect these technologies to be discussed in our class. So, this is a special board which contains micro vias and gold plating, and if you look at your telephone membrane switches, the keypads for telephone switches is all plated with gold. So, this is another board which contains a gold finish. Now, I will show you another board. You can see here this board contains electromechanical components like your fan. That means, just right under the fan there is a active device which will be dissipating a lot of heat. Therefore, as a precaution, this fan is mounted on the top of the device. So, when the board is powered up, naturally the heat will be dissipated, and you can see that the heat is removed quickly from the device as quickly as possible. Because if the device is heated up, then there is a very good chance of the die cracking, and also the substrate, because it is organic in nature, it can warp, it can also melt. Now, I want to show you another example, a building block of a printed wiring board. Now, this is a material that you are seeing here, which is the dielectric material that is used in the build of the printed wiring board. Okay. This is made out of glass plus a organic resin. Now, on top of this, a copper foil like this. This is a copper foil. This will be laminated onto the base dielectric material to give you a board, a rigid board like this. Okay. So, you can expect these technologies to be discussed in our class. We are going to spend more time and in understanding how a PCB or an organic substrate or a ceramic substrate can perform system functions. Okay. So, printed wiring boards are in some sense the heart of the product, and in today's electronic products, a lot of integration goes into making printed wiring board a system level product. So, what is a printed wiring board? A printed wiring board is a substrate which is made up of insulating structure, which I just showed you as an example, with copper foil tracks on its outer surface. The tracks are also formed in the inner layers, right. I mentioned to you, you can make multi layers. So, the tracks need not be on the top and the bottom, they will be inner layers which connect to the top and bottom copper layers, making it a multi layer printed wiring board with very high density. In today's parlance, these printed wiring boards are also known as high density interconnect substrates, HDI, high density interconnect substrates. Now, this printed wiring board, on top of this, so the components are fixed at the top and bottom of the substrate. Okay. The components are fixed to the printed wiring board and connected to the copper traces or tracks by a process known as soldering. Soldering is the process of attaching your components to the printed wiring board or the substrate. So, in this figure you can see devices are mounted on top of the printed wiring board. This is a bare die, this is a packaged die, and in the top figure you can see a very high density substrate, right. It has got different types of components, bare die, encapsulated die, various passive devices. You can see connectors, right. You can see various connectors used at the periphery of the device, and there are some relay type of components which are mounted at the edges, so that you can have access to repair these devices during the working of the product. So, this is the basic definition of a printed wiring board, very simple. I hope you can go through it once again. So, the purpose of a printed wiring board will be to electrically interconnect all the components, mechanical support to the components, powering up the circuit, and it also dissipates heat generated by the components. So, naturally you can expect the dielectric material that is used for the printed wiring board to be somewhat thermally conductive, remove heat to the ambient, to the atmosphere, right. And you can also improve the thermal performance by adding heat sinks. I showed you the other day an example of a heat sink. You can use a heat sink on top of the component, or you can use a fan, or various other methods of cooling are now available. So, if you look at the figure here, from wafer to multi-chip module to board, motherboard and system. So, a PWB should be characterized by interconnection line widths. Just as we are worried about line widths in semiconductor technology, here also we are worried about how much low line widths we can go to, so that you can make it a very high density using very small space. We do not want bulky printed wiring boards to house your products, and that is one of the reasons our components are, the products are shrinking today. If your printed circuit board is going to be huge, then you have to build a mechanical enclosure to suit the size of the printed wiring board. Then we are worried about component density, line pitches and pad sizes, number of pads for connecting various components per square centimeter. This gives you the component density or the pad density. The size of the plated hole or the via. I talked to you briefly about the via or the hole. So, here again, just as the interconnection line width, here also we should be worried about the size of the via. You can't have a very large hole to interconnect layer 1 copper to layer 2 copper, because that will occupy too much of space, and at the same time you are adding more copper than required. So, you should have minimum copper on the board that can perform your system function, electrically reliable system function. Micro vias, do we need it? What are the methods to create micro vias and other technologies? Number of connections per layer. So, how many layers can you have? Can you have 6 layers, 8 layers, 32 layers, 64? We are going to see that. Number of interconnection layers has to be optimized. Efficient board design for high performance and better reliability. I can tell you for sure that any product, if you are doing a PCB design, just as VLSI engineers have spent a lot of time on the VLSI CAD, the PCB design engineers will spend almost 60 to 70% of the product planning time, because the rest 30% can easily be done by fabricating the PCB and assembling it and testing it. The design takes a lot of time. You have to first test it, simulate it, you can probably do some electrical modeling, and then all the corrections will have to be taken back to the schematic, iterations have to be done until you get a very good electrical performance. So, PWB design will take a lot of design time in the industry. So, printed circuit board or printed wiring board incidentally was discovered in 1942 by Paul Eiler of Austria. So, he was using some kind of a organic resin, and he accidentally was trying to image it, okay, and then he was able to find that he was able to transfer the patterns using natural sunlight and some use of some dye which could change the color of the organic resin. Okay. So, that is how patterns were able to be transferred and how we got very good products as a result of this finding. So, after describing briefly about printed circuit boards or printed wiring boards, I will conclude this chapter here, and as I mentioned earlier, printed circuit boards and printed wiring boards will be dealt with exhaustively in the future chapters. So, this is a good time for sensitizing to you at the end of chapter 1 what you can expect in the coming chapters. So, chapter 1 will end here, and I thought I will give some tutorial. Here in this tutorial, I will basically put some questions for you and also try to discuss the answers, so that you will get a very good conclusion or a summary from this entire episode. Next chapter will be on semiconductor packaging. We have seen semiconductors. We will briefly see what semiconductor fabrication would mean, what are the intricacies involved in semiconductor fabrication, and we will have a look at the overview of the process. So, please do some reading on this chapter 1 by using the suggested textbooks given to you in the first introduction class. As I said, even if you can read chapters 1, 2 and 3 of Rao Tumala, which is I told you the prescribed textbook for this course, you will be complete in your understanding about the basic packaging fundamentals. Now, I will begin the tutorial. My first question is, what is a microsystem? Because we have talked about systems, microsystem, nanosystem and so on. So, what is a microsystem and how does it compare with microelectronics? So, the two important things I am asking you is, you must know what is microelectronics, what area it comes under and what is a microsystem. So, I will discuss the answer with you. A microsystem is a micro miniaturized and integrated system based on microelectronics, RF, photonics, microelectromechanical systems and packaging technologies. So, the word integration comes here, it has to be integrated. A microsystem provides a number of integrated functions such as computing, communication, consumer and sensing to serve a variety of human needs. So, you can see here that the word integration is very important, and integration can happen only if we can do or use new packaging technologies. So, a microsystem is synonymous with new packaging technologies and packaged products. In contrast, the microelectronics is based on 3 circuit elements: transistors, capacitors and resistors fabricated at submicron dimensions as an integrated circuit or IC. Okay. So, microelectronics would most probably cover all the aspects of a active device or an integrated circuit. The IC forms the basis for most of today's microelectronic systems, of which computer is a chief example. So, I think you are very clear right now what is the difference between microelectronics and a microsystem, right. Microsystems obviously will include a lot of microelectronics. It is based on microelectronics, out of which the various applications areas will be RF, photonics, MEMS, MOEMs and various other optoelectrical systems and so on. Okay. So, please remember the terms microelectronics and microsystem. The next question that I am asking you is, why integrate microsystem technologies into single products? What is the need for having single products? Does it affect the size? Does it affect performance? So, microsystem technologies, which include digital, RF, optical, MEMS and other sensing technologies, are integrated into single products in order to provide services and functions in the least amount of space and cost, right. This is what I have been emphasizing all along, that when you do a product packaging, you are indirectly doing miniaturization, although you might not be aware of it, but eventually if you choose the best devices or best components available, you will end up with a very good single product which is small in nature, small in size. So, you will end up with the deliverables as least amount of space occupied at the least cost. So, your packaging engineer should look into these two aspects. What is the example? A cell phone is a very good example of a microsystem. It is micro miniaturized, it is integrated, okay, and it has got a computer and a wireless product based on processors, RF passives, MEMS switches, display technology, image acquisition and human interface technology via voice or keypad. It is compact to use, convenient to use, it is cheap to manufacture because of high volume fabrication, right. A cell phone will have a computing, a processor, DSP or whatever it is. It is a wireless product. It has got other processors and controllers. It has got passive devices. It has got display technologies which are current, image acquisition, camera which is very small and which can immediately capture, store and send globally through the network. Okay. So, all of these things are possible with a single product. So, this is a very good example of microsystem technologies being integrated in a single product. There may be different boards which perform different functions, but at the same time they are highly integrated. What is the role of packaging in microsystems? Right. So, we have seen various set functions. Now, let us see what is the role of packaging. Without packaging, does microsystem mean anything? Packaging provides a set of interconnections at IC or device level as well as at the interface and interconnections between ICs, which is at the board level. So, this interconnections between ICs is actually at the board level. Then you have MEMS, photonic, RF and other components into a system level board, right. So, here is where most of the packaging activity that takes place to form electronic products. Historically, these interconnections have been electrical. As microsystem performance increases, we may see photonic interconnections in the near future. So, the important opinion that we should gather from this chapter 1 is that system level boards perform system functions, and for that to happen packaging is very important, because you are using various devices like ICs, MEMS, various other components, and they have to be interconnected, and for that system level board packaging becomes very important. So, the next question is, what is the fundamental building block of an integrated circuit, MEMS, optoelectronics device and RF device? Okay. The fundamental building blocks of ICs are, as you know, transistor, capacitor and a resistor, right. To control the performance of the transistor, you are building in situ during the fabrication of the device capacitors and resistors, and that is how it is built and packaged. The fundamental building blocks of MEMS devices are the cantilever, the membrane, the micromotor, all of which are for the most part electrostatically actuated. We do not have a chapter on MEMS here, but we will try to, we must understand and appreciate that MEMS is a result of very good system level packaging. It is a miniaturized product. The electronics may be very small in MEMS, but at the same time it involves a lot of mechanical performance and actions. The fundamental building blocks of optoelectronic devices are the photonic sources such as the laser, the photodetector and the optical medium such as waveguide. And the fundamental building blocks of RF are the local oscillator, the passive components such as inductors and filters. So, you can see for each of these there are some fundamental building blocks, which I think if you are aware it will be very useful. Now, again in a different type of a question, we have seen in the earlier question the role of packaging and why packaging is important, because it improves the system performance. There is no doubt about it. It reduces the cost, reduces the size and increases the reliability functionality of your product. A good packaging design can make a system successful, because it can also improve avenues for understanding new materials and researching into new processes, whether it is electrical, thermal or pure materials processes. Good packaging process can make a system reliable and inexpensive. After all, finally, we are going to we are understanding packaging to do this. What is that? We have to make a system that is reliable and inexpensive, whatever be the field. Okay. That is the main aim of understanding packaging. Now, I think I have mentioned about this. In the area of packaging, physicists deal with, there can be a lot of physicists working in packaging. They work with issues like semiconductor properties, the mechanism for the electrical conductivity, thermal conductivity of materials, very important in packaging today, because if you want to use, let us say, a material with a dielectric constant of 2.6, then can you really find out how good it is going to be in terms of electrical performance along with copper, okay? Whether it is going to create a lot of crosstalk, noise and other parasitics associated in the electronics domain. Then if you look at materials engineers, like for example, the ceramicists, people who work in ceramics, they deal with the composition and fabrication of inorganic and inhomogeneous matter, because if you want to use ceramic substrates in terms instead of organic substrates, then you need to know the properties of ceramic material like hardness, stiffness, its capability to withstand high temperatures, resistance to chemicals and insulating properties. These are very important from the electrical and thermal standpoint. Computer engineers, of course, they are important in building the architecture of microprocessors and other active devices, and they are also important in the performance of computer systems, reliability of computer systems. Chemical engineers deal with the processing of organic and inorganic chemicals and interaction of liquid, gaseous and ionized reactants with one another and with solid surfaces. Electrical engineers deal with signal and power distribution in systems. When we looked at the definition of packaging, I think I have emphasized about signal distribution and power distribution efficiently in a package, in a system. And for that, you have to also, these electrical engineers should work with materials engineers to get a very good reliable system. Mechanical engineers contributing to packaging can work with thermomechanical design, right. For example, I talked about a package. Now, there is going to be a lot of heat dissipated from this device. Now, mechanical engineers can really tell us what type of heat sink you can place, or whether you can use some convection based airflow mechanism, okay, or whether you can use impinged jet cooling to quickly remove the heat and so on. So, thermal management and as a result thermomechanical reliability and heat transfer are very important areas where mechanical engineers can contribute in the realm of packaging. Why are packaging considerations for automotive electronics different? We have seen this during the examples and the case study. This has got a different set of conditions and requirement. The reason is the difference between this and consumer electronics is that the environment in which they perform makes the packaging activity for automotive electronics very difficult and different. Cost, size and weight reductions are also major factors that influence packaging of automotive electronic products. They are not similar to printed circuit board plastic material, which I have shown, or ceramic units. Okay, so, you have to make a very important decision, can I use a plastic or a ceramic for automotive. Processing is distributed around the vehicle as dictated by locations of sensors and actuators, and packaging requirements are changing accordingly. Okay. So, it is not unique in some sense, it varies from system to system. So, with this our tutorials come to a conclusion for chapter 1, and we will be looking at chapter 2 from now on. The next class will deal with semiconductor packaging and semiconductor process overview. So, I think I hope you have got a very good glimpse about the summary and overview through these tutorials. Please go through these tutorials once again, and then the chapters I mentioned about There are different textbooks apart from Rao Tumala. You can look at R.S. Kanpur, that is also a suggested textbook for this particular course. And in the next class, we will look at chapter 2, which is semiconductor fabrication and packaging. This is our starting point for the next chapter. Thank you so much, and we will meet in the next class.